everyone, welcome back to Measure Theoretic Probability. We are talking about convergence of sequences of random variables. Now, these are not numbers, they are potential wannabe numbers. They may be numbers one day when they're observed, but right now, we can't use our usual sort of delta epsilon definitions from calculus or analysis, but we can if we bring real numbers into the problem by looking at maybe the probability that xn is close to x, and that probability is a number between 0 and 1, but still a number. Or maybe an expected value of xn, even though we haven't dealt with expectations yet in this course. And by the way, that's coming up in the next video. So far, we've looked at one type of convergence for a sequence of random variables known as almost sure convergence or almost everywhere convergence or convergence with probability 1. We write xn converges almost surely to x with this as over the arrow if the probability that the limit as n goes to infinity of xn equals x is equal to 1. As usual, for a probability statement like this, we're really taking the probability measure of a set of omegas. That's the omegas are suppressed here, but this represents the set of omegas for which the limit as n goes from 1 to infinity of xn of omega is equal to x of omega. For each omega, we're just talking about a limit of real numbers equaling a real number, and we do know how to deal with that. It may be that the xn's of certain omegas do not converge to x of omega, but as long as that's only on a set of probability measure 0, we do have almost sure convergence. We then had a criterion for almost sure convergence, and that is that xn converges to x almost surely if and only if the probability that the distance between xn and x is greater than epsilon infinitely often is 0 for every epsilon greater than 0. We proved this last time, and this is a criterion I find really useful, not so much for showing that a sequence converges almost surely or doesn't. Like, I don't want to use this so much, or I don't find myself using this so much in like an exercise, but in proofs where we've got almost sure convergence as part of the setup and we're trying to show something, I do find this criterion comes in handy a lot. We had two other things that we showed last time, and these were not if and only if statements. So the first was that if the sum as n goes from 1 to infinity of the probability that the distance between xn and x is greater than epsilon, if this sum is finite for every epsilon greater than 0, then we do have almost sure convergence. I happen to really like this one because this probability is a number, and this is a nice sum of numbers and feels a lot more tangible, I think, than some of the other methods for showing convergence almost surely. This one works out for me often. But it's not an if and only if statement, and I'll come back to that in a moment. We had a fourth property that looks a lot like this, where we replace this epsilon with 1 over n, but it's not as simple as just using an example epsilon, because it's not like I replace the epsilon with 1 over 10,000. That would just be an example epsilon. By putting a 1 over n in here, note that the sum is running over n, so it's actually, a little bit more different than it might look from this line above. And we proved that both of these are sufficient criteria for almost sure convergence. So when I see a list like this with some if and only ifs and then some one-directional things, first thing I think of is, can we find an example where the other direction does not hold? So we could do this with both 3 and 4, but I'm just going to look at property 3. I want to show that this sum being finite for every epsilon greater than 0 is a sufficient condition to get almost sure convergence. Actually, we've already showed that. We proved that last time. But I want to give an example of it not being necessary. So what do I need to do? I need to find a sequence that converges almost surely, and yet this sum is infinite for at least one epsilon. I don't need it to hold for all epsilon, but I need to exhibit an epsilon for which this sum is infinite, but we do have almost sure convergence. I'm going to go back to what is becoming our new go-to example for these numerical examples. For my space, I'm going to let omega be the real numbers between 0 and 1 inclusive. I'm going to let the sigma field curly f be the Borel sets on 0, 1, and I'm going to let p be Lebesgue measure or length in the reals. I'm now going to define a sequence of random variables. For every little omega in 0 to 1 inclusive, I'm going to define xn of omega to be 2 to the n times an indicator that says that omega is between 0 and 1 over n inclusive. So remember, this function is going to equal 1 if you plug in a little omega in this interval and 0 otherwise. Let's try to get a handle on what this looks like for a particular omega. I'm going to take, just as an example, omega equals 1/3. If I look at x1 of 1/3, this is 2 to the 1 times the indicator that says that 1/3 has to be between 0 and 1 inclusive, which it is. So this indicator is 1. So we get 2 to the 1, or 2. If I look at x2 of 1/3, then the interval in the indicator has shrunk down to 0 to 1/2, and 1/3 is in that interval. So this indicator is again 1. I get 2 squared times 1, or 4. If we go to x3 of 1/3, because of the way I define this with closed endpoints on this interval, the interval is now 0 to 1/3 inclusive. So my 1/3 happens to just fit in that interval. This indicator is 1. I get 2 cubed, or 8, for this value of x3 of 1/3. But x4 of 1/3, now the interval has shrunk so that it no longer includes 1/3. And I don't care what's going on over here with these powers of 2, but the indicator is going to take the value 0 when you plug in little omega equals 1/3. And for x5 and x6, that interval is going to keep shrinking down towards 0, and it's never going to include 1/3 again. So we have a sequence here. For this fixed omega, we have a sequence of real numbers. It's 2, 4, 8, 0, 0, 0, 0, 0, 0, 0. The limit is 0. And this limit is going to be 0 for every little omega between 0 and 1, including 1, but not including 0. We'll look at that separately in a moment. But for any fixed omega that is strictly greater than 0 in that interval, those indicators that keep going from length 1 to length 1/2 to length 1/3 to length 1/4, they'll eventually pass wherever the omega is, and the indicators will end up being all 0 after a point. So we will, in fact, get the limit as n goes to infinity of xn omega will equal 0. The omegas for which this is satisfied is all omegas greater than 0. So that in this case is going to be the interval open 0 to closed 1, which has Lebesgue measure 1 or probability measure 1. And that's enough to say that my xn's converge almost surely to x, where x is 0. So I've got two ways to say this. I could say xn converges almost surely to 0. Or if you'd rather see a random variable there, I could say that xn converges almost surely to x, where x is the very boring random variable that takes on the value 0 with probability 1. So this is a sequence of random variables where we do have almost sure convergence. Remember, we were looking at that property 3 that I started this video with. We're trying to show that a particular given condition about a sum being finite is not necessary to have almost sure convergence. So consider the probability that the distance between xn and x is greater than epsilon. In this case, our x is 0, so this is the probability that the absolute value of xn is greater than epsilon. In this case or example, our random variables are not negative, so I could just drop the absolute value. This is, of course, shorthand for the probability measure of the set of omegas for which xn of omega is greater than epsilon. And if I fill in what xn of omega is, I get an expression like this. Looking at this, I think I want to choose an epsilon between 0 and 2, not inclusive, and here's why. Let's look at this quantity when n is 1. When n is 1, we want the set of omegas for which 2 times 1, because I'll get the entire interval 0 to 1 inclusive. So any omega in there that is between 0 and 1, this is going to be 1. This indicator is going to be 1, and this is going to be 2, and that's definitely going to be greater than epsilon as long as I choose an epsilon between 0 and 2. So this probability is 1. When n is 2, if we look at this set, we've got 4 times the indicator that the omega is between 0 and 1/2, and we want that greater than epsilon. So 4 times 1 is certainly greater than epsilon, but it's only going to be, in fact, this quantity greater than epsilon if the omegas are between 0 and 1/2. So the only omegas for which this quantity is greater than epsilon are the omegas that turn on this indicator, and those are the omegas from 0 to 1/2. And this interval has the Lebesgue measure 1/2. So that's what we get when n equals 2. When n equals 3, we're going to get 2 cubed here and an indicator from 0 to 1/3. And that will be greater than omega only if the indicator is 1 again, and that's only going to happen for the omegas between 0 and 1/3, and the probability measure of that interval from 0 to 1/3 is 1/3, etc. So in general, for n equals n, this probability over here is going to be 1 over n. So if I look at the sum as n goes from 1 to infinity of terms like this, I get a harmonic sum as n goes from 1 to infinity of 1 over n, which is infinite. And here we have it. We've got that this sum of probabilities is infinite, and yet we have almost sure convergence. So this is an example for property 3 on the first slide for today's videos, that this thing being finite is sufficient, but not necessary for almost sure convergence, because again, this sequence does converge almost surely to 0. So let's look at a new type of convergence. It's going to be called convergence in probability. A sequence of random variables xn converges in probability to a random variable x if, for any epsilon greater than 0, the limit as n goes to infinity of the probability that the distance between xn and x is greater than epsilon, if this is equal to 0, again for every epsilon greater than 0, then we have convergence in probability. There's a big difference between this and almost sure convergence. When we talked about almost sure convergence, the limit was on the inside of the probability statement, and now it's on the outside. And this one's a lot more concrete and easy to think about, especially if you're taking a probability course or a mathematical statistics course before measure theory. You can deal with computing probabilities like this and just talk about limits of sequences of numbers. And if the distance between xn and x is greater than epsilon, if that probability is going away, is going to 0, then xn and x are getting really close together, and we say that xn converges in probability to x, and we write xn with an arrow and a p over it to x. Now, if you want to take the complement of this probability so that you have less than or equal to epsilon, then that limit should go to 1. But you also might want to take the inequality as it is, but throw in the epsilon or not. So we've got some cases to consider. And I claim that this can be replaced by greater than or equal to epsilon. It doesn't have to be strictly greater than epsilon. And I don't know if you want to see this, because this is usually in class, I usually say, because, it's for all epsilon. So you could just do a little plus or minus action above and below that epsilon, and it doesn't matter. But also sometimes people ask me, this is one of those things that just seems so believable, but how do you show it? I don't know if you're one of those people, but let's show that this definition and then the definition with a greater than or equal to in here, let's show that those are equivalent. By the way, convergence in probability is sometimes referred to as convergence in measure, really not in probability, but if you're in a non-probability course and you're working with a measure mu, you can have a definition just like this, and it would be called convergence in measure. But let's go back to showing the equivalence between strictly greater than epsilon and greater than or equal to epsilon. So suppose that the limit of the probabilities that the distance between xn and x is greater than or equal to epsilon is equal to 0 for all epsilon greater than 0. I claim that this is equivalent to convergence in probability, or equivalent to the definition where this is a strict inequality. To see this, note that the set of omegas for which xn omega and x omega are greater than epsilon apart is contained in the set of omegas for which the distance is greater than or equal to epsilon apart, simply because there's more chances for this event to happen. If the xn and x are greater than epsilon apart, then they're greater than or equal to epsilon apart, but not the other way around. So there's potentially more omegas in this set. So we have this inclusion here. And now by monotonicity of probabilities, if I take the probability measure of both of these, I get the probability that the distance between xn and x is greater than epsilon is less than or equal to the probability that the distance between xn and x is greater than or equal to epsilon. Let's take limits all the way across as n goes to infinity. On the left side, on the right side, if we're assuming that this goes to 0, then the limit as n goes to infinity of this, which is less than or equal to the limit as n goes to infinity of this, is also 0. And that's the definition of convergence in probability. So we see that putting greater than or equal to epsilon in here gives us the definition with greater than epsilon. Can we go the other way? The other direction is a little more tricky. Let's look at the set of omegas for which the distance between xn omega and x omega is greater than or equal to epsilon. I claim this is contained in the set of omegas for which the distance is greater than epsilon minus epsilon over 2. And this epsilon over 2 could be really anything as long as it brings this number down to less than epsilon and doesn't make it negative. So I just picked something. But if the distance between two things is greater than or equal to 5, then that distance is definitely greater than 4, but not the other way around. And that's why we get this inclusion here. So we've got this set contained in this set. Again, I'm going to use monotonicity of probabilities. The probability that xn minus x is greater than or equal to epsilon is less than or equal to the probability that xn minus x is greater than epsilon minus epsilon over 2. And so if I take the limits all the way across, because I am assuming that this limit holds, then this epsilon minus epsilon over 2 is just a particular epsilon. I've got strictly greater than a number, and this is supposed to hold for any positive number. So we are assuming that this side has a limit of 0, and therefore this side has a limit of 0. And that's what we were trying to show. Starting with this, we get this. And on the previous slide, we show the other direction. So in other words, this is one way to define convergence and probability. This is equivalent. And if you want to turn either of these around so that we're talking about complements, you can have a less than epsilon or a less than or equal to epsilon. But the probability that xn minus x, their distance is less than epsilon, that should be going to 1 because it definitely should be getting small. And no matter what epsilon you pick, that distance needs to be getting below it. So the probabilities of 0 turn into probabilities of 1. So all 4 of these are equivalent ways to talk about, they're equivalent to each other and the definition of convergence in probability. So let's look at an example of convergence in probability. I'm going to take the same space. Omega is going to be the interval from 0 to 1 inclusive. Curly F is going to be the sigma field or the Borel sets on 0 to 1. And P is going to be Lebesgue measure. I'm going to define a sequence of random variables like this. X1 of omega is going to be omega plus the indicator that says that omega is between 0 and 1 inclusive. I'm going to define the next one and the next one so that you see a pattern because this one's a little difficult to write out in a general formula. I'm going to let X2 of omega be omega plus the indicator that says that omega is between 0 and 1/2 inclusive. So it almost looks like I have a nice formula where I'm cutting this interval in half, but that's not what I'm doing. X3 of omega is going to be omega plus the indicator on the interval from 1/2 to 1 of omega. So I'm not just squishing that interval down in a nice recursive way. I'm taking the full interval, then 0 to 1/2, then 1/2 to 1. And the next one is going to be omega plus the indicator that says that omega is between 0 and 1/3. The next one is going to be the random variable is going to be omega plus the indicator that says that omega is between 1/3 and 2/3. And the fact that I have some overlapping endpoints of these intervals is not really important because we're deriving a sequence that hopefully is going to be converging in probability to something. And so we may have that our sequence is constant for a while, like this indicator is 1 and the next indicator is 1 at the same time and the next one. You'll see, we're going to put some actual numbers in here and take a look. So 0 to 1, 0 to 1/2, 1/2 to 1, 0 to 1/3, 1/3 to 2/3, 2/3 to 1, 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1, and so on. This one's a little hard to write down with a general formula. Now, I haven't given you an X to say, show this converges in probability to X, but what might you guess that this limit would be? These intervals are jumping around, but they are shrinking. So it seems like the omegas will eventually not be in the interval and that all of these indicators, or a lot of these indicators, infinitely many of these indicators are going to be turned off and 0. So you might guess that this sequence is converging in some sense to the random variable x of omega equals omega. That's a reasonable guess. Let's look at some concrete values. I'm going to plug in little omega is 0.28. Now x1 of 0.28 is 0.28 plus 1 because the indicator there is 0 to 1 and 0.28 is between 0 and 1. So that indicator turns on and is 1. and we get 1.28. x2 of 0.28 is going to be 0.28 plus 1 because 0.28 is between 0 and 1/2. X3 is going to be 0.28 plus 0, which is going to be 0.28. X4 is going to be 0.28 plus 1. So go back and look at the previous slide, or if you've written that down, it's easier for you to check this. It's kind of annoying if I keep just saying these intervals really fast. But what's happening is that the indicators that are indicating that we're in certain intervals, they don't just shrink away from an omega. They move and they move again and they move again. So a lot of these indicators are going to be 0, but they're not going to be 0 from any point on out. As we keep chopping up the intervals, we'll catch that 0.28 in the future. And so this limit actually does not exist. We get 1.28 sometimes, we get 0.28 sometimes, but it just keeps sort of flipping around. Limit does not exist for this little omega. And in fact, it does not exist for any omegas between 0 and 1 inclusive. So this was supposed to be about convergence and probability, but what we've just seen is that this sequence does not converge almost surely to anything. Hopefully it converges in probability to something, or this was a really bad example. As I was saying, the length of these intervals and these indicators is going to 0, and we were kind of guessing that maybe it was converging to x of omega equals omega, and in fact, it is in probability, so let's check this out. Let's take any epsilon greater than 0 and look at the probability measure of the set of omegas for which the distance between x and x of omega is greater than epsilon. If I just plug in what these are, this is an omega plus an indicator, and this is just omega. So those omegas are going to cancel, and we're going to be left with just the indicator. I'm going to write this as a set of omegas such that the indicator that omega is between an and bn inclusive is greater than epsilon. I don't have a formula for an and bn, but we know there's some endpoints, and we know that they are coming together because we keep getting smaller and smaller intervals, smaller and smaller subintervals of the interval from 0 to 1. I have a couple of cases I need to consider here. This indicator is going to be 0 or 1. So if epsilon is chosen between 0 and 1, this indicator is going to be greater than epsilon if and only if the omega is between an and bn. And the probability measure of this interval is the Lebesgue measure, the length, bn minus an. And again, these are endpoints of intervals that are shrinking to 0. So the limit of this is 0 as n goes to infinity. Another case, which I didn't write here, but we do need to consider, is if epsilon is greater than 1, because we need this thing to hold for all epsilon greater than 0. If epsilon is greater than 1, then this indicator being either 0 or 1 is never greater than epsilon. So the omegas for which this inequality holds is the empty set, and that has probability measure 0. And the limit of zeros is a 0. So in either case for epsilon between 0 and 1 or greater than 1, even though I only wrote one case here, the limit of these probabilities are 0. That's the definition for showing that xn converges in probability to x. At the same time, this was an example where we did not have almost sure convergence. One more time, this is an example of convergence in probability, but not almost sure convergence, but I claim the other direction does hold. If you do have a sequence converging almost surely, then you do have convergence in probability. For this reason, we say that almost sure convergence is a stronger form of convergence. If you have almost sure convergence, you have convergence in probability, but not necessarily the other way around, as we have just seen in an example. Let's prove this claim. I'm going to use my favorite equivalent criteria for almost sure convergence. It was property 2 on the first slide today. Recall that if we have xn converging almost surely to x, then we have, for any epsilon greater than 0, the probability that the distance between xn and x is greater than epsilon infinitely often must be 0. Infinitely often is a limb soup kind of thing. We can write this as the probability measure of the limb soup of some an's is 0, where an is defined to be the set of omegas for which xn omega and x are greater than epsilon apart. This is a direct consequence and indeed equivalent criteria to almost sure convergence. Now I'm going to ask you to recall something from way back. I believe this is in video 9 when we were talking about continuity of probabilities. This is not exactly continuity of probabilities, but it was right next to that concept. We showed that the probability that the lim-inf of ANs is less than or equal to the lim-inf of the probability of ANs is less than or equal to the lim-sup of the probability of ANs is less than or equal to the probability measure of the lim-sup of the ANs. Again, I think you're going to find this back in video 9 or really close to that. So if I start with the assumption that I have almost sure convergence, then I have this probability is 0, which is the same thing as saying this is 0, which is the same thing as saying this is 0. And all of these being probabilities are not negative. So that forces every one of these to be 0. In particular, it forces these two guys in the middle to be 0. The lim-inf of the probability of the ANs is equal to the lim-sup of the probability of the ANs is equal to 0. And when the lim-inf is equal to the lim-sup, that's how we define the limit. It's existing and equaling 0. So we now know that the limit as n goes to infinity of the probability of an exists and is 0. But what was an? An was the set of omegas for which xn omega minus x is greater than epsilon. So we've shown that the limit as n goes to infinity of the probability measure of the distance between xn and x is greater than epsilon is 0. And this is one of our definitions for convergence in probability. One more time. Convergence almost surely implies convergence in probability, but not necessarily the other way around. And so for this reason, we say almost sure convergence is a stronger form of convergence, and convergence in probability is weaker when compared to almost sure convergence. In the next video, we're going to talk about some subsequent stuff. For example, if you have a sequence of real numbers that converges, like let's say lowercase an converges to a real number a, then every subsequence is going to have to converge. Think of a bunch of numbers sort of funneling down to be collected around a, and if you sort of delete any ones that you want to delete and only pick a subsequence, they have to funnel to the same place. We're going to get the same result for convergence and probability and almost sure convergence. Whereas you can have a sequence of real numbers that is not converging to something, but you can find a convergent subsequence. In fact, we have the famed Bolzano-Weierstrass theorem from analysis that says that if you have a sequence of real numbers and it's bounded, then you definitely have a convergent subsequence. I want to look at statements like this next time with almost sure convergence and convergence in probability, and hopefully get to defining expectation. If not, I promise it will be in the very next video. So I hope to see you in the next one.